4.5.3 Wave-particle duality. Erwin Schrödinger was an early 20th century polymath, lover of cats. Was an early pioneer in the field of feline psychology, following on from the work of Sigmund Freud with humans. He dealt with the deep-seated existential crises that he observed with his cat, Chairman Meow, who he observed suffered deeply from worries of its own. It was often confused as to whether in fact it was alive, dead, or a superposition of both. He also dabbled in the field of quantum physics, and during a holiday to Copenhagen developed an experiment to solve his cat's problems. So, red laser diffraction. You can see here a red laser is creating a diffraction pattern not too dissimilar from Newton's rings, and as we are aware, this is only observable with waves and is evidence that light is a wave. Recently, we studied the photoelectric effect and showed that was evidence of the quantization and particle nature of light and is only explainable by the photon model. So we end up with this dichotomy that light is both a particle and a wave, depending on the phenomena which we are choosing to explain. So the electron gun or cathode ray tube. So initially we have a high energy beam of electrons, which are called cathode rays, because they were emitted from the cathode. And we can show that if that is incident on a graphite screen, we can then produce a diffraction pattern from those rings we just saw with a red laser light. Now, cathode rays were fine, and if they were distinct from electrons, that we didn't have a problem with that. But it was later shown that the cathode rays were actually a beam of electrons, which classically are a particle, but we could show that cathode rays were easily deflected by magnetic and electrical fields, which indicates that they were actually a beam of electrons. So we've got the similar problem to that which we have with light, that electrons apparently appear to behave as waves, as well as behave as particles, depending again on the situation we are in. A French chap, De Broglie, studied this in a bit more detail and showed that just like light exhibits both wave-like and particle properties, so do fast-moving electrons. He showed that the wavelength of those electrons is proportional to the inverse of their momentum through various studies, and obviously faster the electrons move, the greater the momentum, and therefore the shorter the wavelength of those electrons. The de Broglie wavelength, lambda, is just equal to Planck's constant divided by the momentum of the electron. Back to Erwin Schrödinger. So, the Copenhagen interpretation was an agreement made by various different scientists in the early 20th century that sort of solved this problem of wave-particle duality, that both light and electrons appear to exhibit particle properties in some circumstances and wave properties in others. And the gist of it is stuff arrives and departs as particles, but travels as waves. So how can electrons be a wave? Well, Schrödinger comes up with his famous wave equation, which basically says that electrons are a probability wave. As soon as you stop measuring them, i.e. they are traveling from one place to another, then they become a probability distribution, and that probability distribution is a wave. One could imagine this a bit like tossing a coin in the air. You know whether it's a head or a tail the instant you throw it into the air. Whilst it is spinning in the air, it is arguably both a head and a tail, and only becomes one or the other when you then catch it and look at it. I.e., you collapse the wave function when you look at it, it stops spinning, and then you know. So we call that collapsing the wave function. The act of measurement collapses the wave function. Now, Erwin Schrödinger then got into some trouble with the Austrian wing of the RSPCA when attempting to explain this to some of his students. So if we take a cat and we place that cat in a box along with a radioactive source. Now, this radioactive source will occasionally decay, but is a quantum object, so will only decay at random. Now, if it decays, it will produce a beta particle. That beta particle triggers a mechanism which smashes some cyanide and will kill the cat. Equally, if it doesn't decay, it won't trigger the particle and it won't kill the cat. So we have a dead cat in the circumstance of the radioactive decay occurring, and an alive cat if the radioactive particle doesn't decay. The issue is, until you open the box, you will only at that point collapse the wave function and measure the problem and see whether your cat is dead or alive. So arguably, if you don't open the box, your cat could be both dead or alive. It's in a superposition of both dead and alive states. And this habit of putting cats into boxes unfortunately got Erwin Schrödinger in a lot of trouble, and he ended up serving time for cruelty to animals.